Good morning to all. Myself Sayan Khewal from BTech CSE, second year, Computer Science and Engineering from VIT, Chennai. Today I am going to speak on the topic Turing machine. Let's start. Introduction of a Turing machine. A Turing machine is a mathematical model proposed by a British mathematician Alan Turing in 1936. It is a theoretical device that consists of a tape, a read-write head, and a finite control unit. The Turing machine was introduced as theoretical model of computation to explore the limit of what is computed by a machine. The, the concept of a Turing machine is central to the development of the theory of computation and the study of algorithms. The idea of the Turing machine is still widely used today in computer science and is an essential tool for understanding the limits and possibility of computations. Definition of a Turing machine. A Turing machine consists of a finite set of states, including an initial state and one or more accepting or rejecting state. It also has a finite set of transition rules that determine the next state of the machine and the symbol to be written on the tape, given the current state and the symbol under the head. A Turing machine can compute any function that is computable by an algorithm, making it a powerful tool in theoretical computer science. Turing machines are used as a theoretical tool for analyzing the limit of computation and studying the complexity of algorithms. They are also used in practicing for designing and analyzing computer programs, especially those involving repetitive or iterative processes. Now let's discuss the components of a Turing machine. The components of a Turing machine are a finite set of states, a tape, a read-write head, a transition function, an alphabet, an input and an output. Now let's discuss the representation of a Turing machine. A Turing machine can be represented formally as a 7-tuple, namely Q, sigma, rho, delta, Q0, B and F, where Q is a finite set of state, sigma is the finite set of input symbol or the input alphabets, rho is the finite set of tape symbol or the tape alphabet, where B belongs to rho and B represents the blank symbol. Delta is the transition function that maps Q cross rho to Q cross rho, where L represents the head moving left and R represents the head moving right. Q0 is the initial state of the machine. B is the blank symbol, which is a member of the tape alphabet rho but not included in the alphabets. Sigma is the set of final or accepting state of the machine. Working of a Turing machine. The working of a Turing machine can be explained in the following steps. Initialization. The Turing machine is initialized with an input string in its tape and the read-write head is positioned to the first symbol of the input. State transition. The Turing machine reads the symbol under the head and consults its transition function to determine the next state of the machine and the symbol to write on the tape. The transition function also specifies whether the head should move to the left or to the right of the tape. Write or move. The Turing machine writes the symbol on the tape, move the head to the next cell on the tape according to the transition function and transition to the next state. Repeat. Step 2 and 3 are repeated until the Turing machine reads a final or accepting state or a rejection state. Output. If the Turing machine reaches a final or accepting state, it halts and outputs the final string of symbols on the tape. If it reaches a rejection state, it halts and rejects the input string. Acceptance and rejection of a string by Turing machine. The Turing machine accepts or rejects an input string based on the final state that performs the computation. Acceptance. The Turing machine reads the input signal from the tape and performs a sequence of state transition based on the input symbols. At the end of the computation, if the Turing machine reaches a final or accepting state, it accepts the input string. Whereas rejection, If a Turing machine reaches a rejection stage after processing the input string, it rejects the input string. This means that the Turing machine does not recognize the input string as a valid string of the language defined by the Turing machine. Now let's discuss an example of a Turing machine. So the example is design a Turing machine to recognize language of string in the form 0 raised to the power n, 1 raised to the power n, and 2 raised to the power n. This is a language that is not CF and cannot be accepted by a PDA. Starting from state 0, we erase the leftmost 0. In state 1, we then skip over the remaining zeros, excepting to hit a 1. When we see a 1, we replace it with a x. In a state 2, we then run back to the left end of the string and return to state 0 so we can repeat the whole process. If in state 0 we are looking for an x, we make one last pass over the string to make sure we have no ones remaining. The Turing machine inserts an additional state q5 that does the input of 2, which states q2 does the input of 1. In essence, we implement a new algorithm. Starting from state 0, we erase the leftmost 0. In state 1, we skip over the remaining zeros, excepting to hit a 1. When we see a 1, we replace it with a x. In state 2, we continues moving to the right, skipping over any ones we encountered. When we encounter a 2, we replace it with a x. Then run to the left end of the string and return to the state 0 so we can repeat the whole process. If in the state 0 we are looking for an x, we make one last pass over the string to make sure we have no 1s or 2s remaining. And on the left side you can see the state diagram for the Turing machine. Halting problems in Turing machine. The halting problem is a classic problem in computer science and is related to Turing machine. It was first introduced by Alan Turing in 1926 as a part of his work on the foundation of computation. The halting problem asks whether it is possible to write a program that will determine whether any given program running on any other given input we eventually halt or run forever. The answer to this halting problem is that there is no such algorithm. This was proven by Turing himself using a technique called diagonalization. The proof is a fundamental result in computer science and has important implications for the limits of computation. The halting problem has important implications for the theory of computation as it shows that there are some problems that cannot be solved by an algorithm or computer program. This result has important application in fields such as cryptography, where it is used to design secure encrypted algorithms. Limitations of a Turing machine. While Turing machines are a powerful tool for analyzing algorithms and problems, they do have some limitations. Some of the limitations of Turing machine are: Turing machine model is idealized, not suitable for analyzing space complexity, cannot solve undecidable problems, not efficient for large input size, not capable of learning. Application of a Turing machine in theory of computation. Some of the key applications of Turing machine in the theory of computation are: formal language theory. Turing machines are used to define and analyze formal language, which is a set of strings over a given alphabet. Computability theory. Turing machines are used to study the concept of computation, which is concerned with the help of problems that can be solved by algorithms. Complexity theory. Turing machines are used to analyze the time and space complexity of the algorithm. Compiler design. Turing machines are used in the design of compilers, which are programs that translate high-level programming language into machine code. Artificial intelligence. Turing machines are used in the field of artificial intelligence to study the concept of machine learning. Thank you.